In this video, we're going to use the derivative rules that we just learned about to find out some stuff about a function. So in particular, remember that the derivative tells us the slope of the tangent line to a curve at any point. So we're going to use our rules now to find the equation of some tangent lines and also find where the tangent line is horizontal. So here's just a meme over here about a little reminder of what a tangent line is, right? What we do to find it the long way is take secant lines through some points that are getting closer and closer together. And then once it hits that single point, right, that becomes a tangent line. And the powerful thing about the derivative is that it gives us the slope of a line through one point, which is amazing. Particularly that we have such simple rules that we learned about just a little bit ago, and we can use those to find out this information. So let's look at f of x equals 3 minus, parentheses, x minus 3 squared. In part A, we're going to find the equation of the tangent line at the point 2, 2. And in part B, we're going to find where the tangent line is horizontal. So I have the graph here of the function. Okay, so this is a graph of the function that we're given, 3 minus x minus 3 squared. It's an upside down parabola. In part A, we're going to find the equation of the tangent line at 2, 2. Okay, so this is just to give you a sense of what we're doing. This isn't how to do it. We want to be more precise than this. But there's the point on the curve, 2, 2, right? And of course, here's what about what the tangent line might look like. Something like that. But we want the equation of it, right? So we're going to use the derivative to help us with this. And then we want to find where the tangent line is horizontal. So remember, horizontal lines are like this. They are flat. They're like the horizon. Their slope is equal to 0. Right? So you can maybe see from the graph where that will happen. It looks like those happen right when we have a positive slope tangent line. Here there's another positive slope of tangent line. Over here it's negative. Here it's even more steeper, but negative. And right about somewhere here in the middle, we have this horizontal tangent line. So it looks like right here is where the tangent line is going to be just flat, right at x equals 3. This isn't the answer to the question necessarily. We want to do this algebraically, but you should always, just kind of get a sense of the situation by looking at a graph, because it can be extra, helpful and affirming that what you did is right, or maybe they tell you that you made a little mistake somewhere and you've got to go back and look for it. So for both of these, we're going to need to find the derivative. So let's find f prime of x. The first thing we want to notice is that in our function here, we don't know how to differentiate something that looks like that. So we're going to need to rewrite this function in a way where we don't have that x minus 3 to the second power. Right? If it were just x to the second power, that's fine, but it's not. It's x minus 3 to the second. So the gist of this is just basically expand, like FOIL out, and get it to look like a polynomial that we are used to seeing. Okay, so f of x. Okay, no derivative yet, just rewriting. I'm going to FOIL out this x minus 3. So it's x minus 3 times itself. So that's x squared minus 6x plus 9. We're subtracting all of that, so we have to distribute the minus sign. And then lastly, I think we can combine the 3 and the 9 together. 3 minus 9 gives us negative 6. So there's the polynomial that we're looking for. This one is, we can definitely differentiate this, right? So let's find the derivative now. Okay, we have negative x squared. So that's really like a negative 1 in the front of the x squared, a negative 1 of a constant multiple of negative 1. So we have negative 1 times the derivative of x squared, which is 2x to the first. Then we'll add the derivative of 6x. Using our sum and difference rule, we can just find the derivatives of each of these three pieces and then add or subtract them, right? So 6 is another constant multiple. So we'll multiply that by the derivative of x. And again, that's just 1, right? That'll be 1 times x to the 1 minus 1, or 1x to the 0, which is 1. Then we have minus the derivative of 6. 6 is a constant all by itself, and so its derivative is just equal to 0. Now simplifying this, we have negative 1 times 2x, so that's negative 2x, plus 6 times 1, which is 6. Okay, now remember that what we have here is a formula for slope of the tangent line. We want the equation of the tangent line. We want the equation of that blue line that we drew. So what this derivative is going to tell us is the m in our tangent line formula, right? I mean, what we're looking for here, again, the equation of the tangent line. This is going to look like y equals mx plus b, where the m, or the slope, is given to us by the derivative, evaluated at 2. Okay, so for part A, okay, we're looking for y equals mx plus b. We need m. Again, that's given to us by the derivative evaluated at the point that we're interested in, and that's 2. So f prime of 2. So we're going to plug in a 2 into the derivative. So it'll be negative 2 times 2 plus 6. Negative 2 times 2 is negative 4. Add 6 to that and we get positive 2. So that's the slope of the line that we have here, positive 2. We also need to find the value of b. To find b, if you have a way that you like to do this, go ahead. There are a few ways you can go about this. I like to plug in a point into our function, or our line. All right, so just put our m in, and then plug in the point. So we plug in a 2 for y and a 2 for x. So we have 2 equals 4 plus b, so b is equal to negative 2. So that means that the equation of the line that we're looking for, the equation of that blue line, is going to be y equals 2x minus 2. That's the equation of our tangent line at the point here, right? So the blue line here has the equation y equals 2x minus 2. All right, for part B, we want to find where the tangent line is horizontal. So again, what that means, a horizontal line, this means that the slope is equal to 0. So here we know the slope, but we want to find where that happens. We want to find, so where in math, this means x. What x value? What x value has a slope of 0 for the tangent line? Okay, so we know that the slope is equal to 0, so we want to solve for x by setting the derivative equal to 0. Okay, so if our derivative formula is negative 2x plus 6, we're going to set the output of the derivative, which again tells us slope. We're going to say, okay, slope is 0. What x value makes that happen? So we can just rearrange this and solve for x. So maybe we'll add 2x to both sides, plus 2x plus 2x. Right, we'll get 2x on the left equals 6 on the right. Then we'll divide by 2. And of course, that gives us x equals 3. Not surprising because that's what our graph showed us. But this actually shows that we were not deceived by our graph, right? It actually is x equals to 3. And this also tells us another thing further, that this is the only place where the tangent line is horizontal, is at this point x equals 3. And we're going to have a whole section, a few sections dedicated to finding where the tangent line is horizontal, because what that shows is a place where your function has a peak or where it turns around. And if you think about applications to that, right, where a function has a maximum, or if it were, opening upwards like this, where it has a minimum, then, I mean, that's a really important question, right? Where do you maximize something or minimize something? So, but for now, we're just kind of focusing on graphical stuff. So horizontal tangent lines are interesting because of what they are, of course. Okay. Example number 2. Oh, I wanted to change this. Sorry about that. So let's make this x squared times x squared minus 4 in parentheses, and then all of that plus 4. So that's the curve we're going to look at here. That's the curve that I have graphed here. It's got this weird W shape. We want to find where this curve has any horizontal tangent lines. So maybe you can tell from the graph, right, where those places are. Take a sec to try to locate them. Just visually. Right, I can see 3. Right here, right here, and right here. Now, this one right here is pretty obvious that that's x equals 0. However, these ones here and this one here, they're in between 1 and 2, or -1 and -2. And it doesn't even look like they're at a half or anything. So we're going to need to find these algebraically for sure to figure out what the exact values are. So again, horizontal tangent lines, this means this means set derivative. I guess instead of f prime, we'll have y prime this time. Set y prime equal to 0 and solve for x. And that's the idea with horizontal tangent lines. We know the slope. We want to find where that slope happens. So it looks like we're going to need to find y prime. However, our y, again, has a product here. We need to get rid of that product using algebra. So we want to rewrite the function without a product. So in other words, just distribute that x squared into the parentheses, right? So if we have y equals x squared times x squared minus 4 plus 4, we'll just distribute the x squared into here and here. Okay, that'll give us x to the 4th minus 4x squared, and then plus 4. We have successfully rewritten this without a product. Okay, now we have a polynomial, or at least, it now looks like a standard polynomial. So now we can find the derivative. Now we can differentiate this. X to the 4th, well, why don't you go ahead and find the derivative of this. Pause this. Make sure that you can differentiate something like this. Okay, x to the 4th's derivative, that'll be 4x to the 4 minus 1, which is 3. Then we're going to subtract the derivative of 4x squared. Okay, so that 4 is a constant multiple, so that 4 is going to stay and multiply by the derivative of x squared. Okay, that's 2x to the 1st. Then we add the derivative of 4. That's a constant all by itself. So when it differentiates, it just disappears. It just goes away. So that's plus 0. Now simplifying this gives us 4x cubed minus 8x. So there's y prime. Now we haven't answered the question yet, right? We want to find the locations or the x values, and find where this curve has horizontal tangent lines. So we're going to set y prime equal to 0 and solve for x. Okay, so we say 0 equals 4x cubed minus 8x. Now to solve any equation where you have an x in more than one place, here we have x cubed and x to the first. The thing that you want to do always, 100% of the time is factor. So on the right-hand side, this is a cubic, but it's got a GCF of a 4x that we could take out. So if we factor out a 4x, we'll be left with x squared minus 2. Now x squared minus 2 is not, it's a difference of two squares, but that's not right. Sorry, I was trying to say it's not a difference of two squares. It's a difference of two things, but it's not a difference of two squares. So I don't think that we can factor further. So all we need to do now is set each of these factors equal to 0. So we'll set 4x equal to 0. And we'll set x squared minus 2 equal to 0. 4x equals 0 when x equals 0. X squared minus 2 equals 0. Well, here we only have an x in one spot, right? We don't have an x appearing to different degree in a different area. It's just x squared. So when you're trying to solve something like this, here's when you can isolate the x, or in this case, x squared. So if we add the 2 over, we get x squared plus 2. If we take the square root, we get x equals positive square root of 2. And don't forget that we'll get x equals negative square root of 2. Because when you apply a square root to both sides, you get a plus and a minus as your answers. Right? If we plug either of these in and square, we'll get positive 2 out. So we need to always make sure that we are aware of that. So looks like that's it. We have x equals root 2, x equals negative root 2, and x equals 0. So checking back in with our graph here, I think we can see here's the x equals 0. And then it looks like that root 2 and negative root 2, I mean, that's nice. We have that symmetry we can see. And I guess that place here, its exact value is the square root of 2. And then over here, that other place of a horizontal tangent line is x equals negative square root of 2. So this is one of the kind of major applications of the derivative so far, finding equations of tangent lines, like in the first example, and finding where the tangent line is horizontal, like in this example and in the first example. In the next video, we'll look at one application that's a little less graphical and a little more real-worldy. So I'll see you then.